Okay, so yeah, here we are today. It's the 25th. Reminders about the Furlough Day Friday, and so the movie reviews for Monday, and homework, and was 3. Also, a lot of stuff on Monday. Do we have questions on the homework thus far? Yes. Yeah. Can I hear them? I'll have a copy of the book. 6.2, number 1. Right.
Yep. I like physical things. Or do they only have hard copies in the stores?
The one I found was a hard copy. That was the cheapest one to get. Certain vehicles, they don't make paper copies. It's always interesting to see which one they do. But yes, I like it.
Okay, so this was an actual problem for Fibonacci himself. It's one of the exercises he gave people to figure out how to use an abacus, apparently. Because it's from the Liber Documents. So 2 birds start flying from the tops of 2 towers that are 50 feet apart. One tower is 30 feet high, the other is 40 feet high. I believe we should make ourselves a diagram. Set the data marker for that. Yeah. So the distance between these towers is 50 feet. Well, that's not working for us. There are. Oh, goody.
Don't put that one down, throw it out.
I'd like to leave it there for the next guy. We got 2 towers, like this and like this. One's 30 feet tall.
Yep.
Yeah, 30. The other is 40 feet tall. And it's 50 feet in between. That's our picture so far. And then we have birds. They start at the same time and flying at the same rate. The birds reach a fountain between the bases of the towers at the same moment. So how far is the fountain from each tower? What they're trying to tell us with the birds thing is that there are 2 lines that have the same length that go down to this tower. Does everybody see that? Yeah. So I don't know where the tower is, the fountain is down here, but the hypotenuses of these right triangles are both the same. You got the diagram right? Okay, great. So how far is the fountain from each tower? X is definitely going to be bigger than 40, isn't it? Because it's a side length of a triangle that includes a side of 40. You use Pythagoras. Okay, so we need a name for the other sides of these triangles. We've got 30 as an upright and 40 as an upright. We've got X as hypotenuses. Hypotenuses. Is that right?
Just assumed it was a right angle. He didn't say it was the leaning tower because
so we assume they're vertical now. Okay, so how about we call this length A and this length B? Then yeah, you've got the Pythagorean relationship that 30 squared plus A squared will be equal to X squared. And then the other Pythagorean relationship is 40 squared plus B squared is equal to X squared. But then you also have the relationship between A and B that they add up to 50. So far so good? Alright, so this is what in modern terms we would call a linear constraint. This is a constraining condition that relates one variable to the other. In effect, it's something that tells you, you really don't need B. B is sort of extraneous, because if you know what A is, you know what B is from that relationship. So this allows you to solve for B in this constraint. It's 50 minus A, and thus you can replace that B with something that involves A. I'm not actually working in red here. Let's see. So, by the way, both of these Pythagorean relations have x squared on their left side. So what I would do is say, since you've got two expressions that are both equal to a third thing, use one of Pythagoras' or Euclid's basic ideas. The two things that are equal to a third are equal to one another. So we get that 30 squared plus A squared is equal to 40 squared plus 50 minus A squared. Well, that's a quadratic formula with A's. Maybe we can solve for A. So let me work on it a little more. 900 A squared equals 1600 plus, square this whole mess out. It is 50 times 50, that's 25 with 2 zeros. Minus 50A, and then another minus 50A is 100 A's with a negative sign, and plus an A squared. One of them there. Oh, I'm sorry. Did anybody see what error I made on the left side? Yeah. Just leave me hanging. You can fix that.
We're yell eventually.
Maybe not. Because I was like, whoa, wait a minute, we've got just an A squared here, and there's 900 A squares there. It was a real brain error, not just a typo. Yeah, so what's going to happen, we can cancel off the A squared on both sides of this. And in fact, what we've got is a linear equation in A. This is going to be easier than I thought. 16 and 25 adds up to 41.
Yep.
And I want to take those to the other side. No, I want to take... Let's just do it a step at a time. Now take the 100A to the other side and then subtract 900 from both sides. So we get 100A equals 4100 minus 900, which is what, 3200. So A is 32. You want to get A equals 32? So the way this is drawn, I guess it's a little bit weak. I think this point is actually more like around here, about 3/5 of the way across, a little more than 3/5 of the way across. So this line and that line are really the two things of equal length. But actually, I think the diagram helps. It sort of lets you know, okay, we're dealing with right triangles. For me, the thing that was the key to unlocking this is noticing the statement about the birds flying at the same rate and reaching the same point was really telling you about these diagonal lengths being equal.
Make that connection.
Yeah.
I was a little ashamed of myself. I was like, this took me too long to figure out that that just meant that the lengths were equal.
I guess that probably was maybe part of the social milieu then, that they would have said things in terms of the flights of birds.
I have figured that part out, but for some reason I wasn't thinking about the fact that those two equations would have been equal to each other. That's the part that...
That's the okay. So one of the things that's funny is you think X is part of the answer, right? You want to know what X is, but it doesn't ask about X specifically. Well, we usually just see we've got all these variables, we want to know what they all are. Do I know what X is at this point?
You can figure it out.
I'm just ignoring it. Yeah, we could go back and figure it out. But
When I first did this, I would say, oh, it's a triangle. When you do triangle function, this I was trying to solve for that.
true. Okay, so, but with trigonometry in the 1400s, they did have trigonometry. In fact, they had spherical trigonometry, which is really a crazy hard subject. But
They had that before triangular.
well, they had it later. Regular trigonometry geometry was developed in the Middle Ages because people needed it for navigation. Right? So the spherical trigonometry was really needed to set ships. It wasn't in a modern form yet, and I found an interesting point of language. You know the name of the function sine? That comes from an Arabic word. It was mistranslated. What it means, literally, is a fold in cloth. Or, in one translation, bosom, a woman's cleaver. And so that kind of fold in cloth got turned into the name for the graph, the Wheeler graph. You
Yeah,
Dr.
Dr. G told me.
Dr. G.
Yeah. We
So,
were in House 1, and he gave us a little lesson of the origins of sine and cosine.
Well, cosine's easy, because once you've got sine, cosine is just the sine of the complement. That's why
No,
it's cosine.
the origin of the word.
The origin of the word for cosine comes from the same word.
Yeah.
It's just throwing a co in front of sine.
Yeah.
Where does secant come
Secants are,
from? Well, the word, not the concept.
so, but the word for that trig function comes from the concept. It's the slope of a secant line, if you look at the diagram for the unit circle. Anyway, is that good to get started on this? Do we need to do any more of these classes? Do you on your own? Yeah.
Just do it.
Yeah, you should have this done on Monday, because this is where the quiz is. So if over the weekend you get time to spend a bit more effort on these, we'll probably come in with questions on Monday. We'll go through that stuff first before we do any quiz. So, slide rules. I have a lot of them here. I don't know if we'll have enough for everybody. Would you mind passing them around? Some of them are in little containers. Make sure, open it up and make sure you're not picking up an empty container, because that makes a thing. While she's doing that, I'm going to show you this item, which is my prized possession. I got this on eBay for $44. It should. Imagine what it costs to ship a thing like this. This is a model of a slide rule. Almost every high school classroom would have had one of these hanging up in the corner next to the top of the chalkboard. And just like I get the calculator out sometimes and put it on the overhead so you can see what I'm doing. Sometimes when you were students that had to learn to use slide rules, you needed to watch the professor set up a problem on the slide rule. So it's big enough that, can you see the pulpit from the back of the room?
Yeah.
That's the point. It's big enough that you can make it out pretty well from the back of a usual classroom. You'll notice that the scales all have labels back here of this sketch. So we got the K scale, K for cubic, because they couldn't spell. K because the person who invented the slide rule, the modern version of the slide rule, was French, but his last name was Mannheim. Remember we talked about that last time? Mannheim is a German surname, and K is cubic in German. Yeah, you get the A and the B scales, which just mean A and B. These are the logarithmic scales. So if you get your slide rule, if you get a copy of this, if you get a slide rule in your hands, you should look around on it and try to find the ones that are labeled A and B. That's what you use first. You may sometimes use C and D. I like to use A and B, but other people, you get a little bit more accuracy with A and B. I think I just said that wrong. You get a little bit more accuracy with C and D, but it's not enough to make much of a difference. Why is my screen blank after 10 seconds? That's not enough. All right, so looking at the A scale, you'll notice that it begins with a 1, and that is because the log of 0 is 1. You know this is a fact. If you you'll see there's tick marks, and you can tell that the divisions are getting closer and closer together, I think. When we get to the next numbered thing, it says 2 on it. Makes sense, 2 follows 1. Notice that from 2 to 3, though, I'm showing, it's about the distance between it's about the width of my fist, right here, is much longer than the distance from 1 to 2, which is, I had to stretch to get that. So 1 to 2 and 2 to 3 are really the same scope in terms of the difference between the numbers, but on the scale, they have gotten shorter. And then 3 to 4 is much shorter, 4 to 5 is even shorter. Here's 6, 7, 8, 9, and there's that number. It's labeled with a 1. Well, what is it really? Uh-huh. And then, what's that one? There's a 2 on it. Oh, you're very clever, 20. Okay. Not 12. Can you find where 12 would be? You'll see that the divisions between numbers that are non-labeled come in what are called major and minor subdivisions. There's some that are a little bit longer and some that are a little bit shorter. And between 10 and 20, you're going to see 10 major subdivisions. That'll be 11 through 19. I guess you actually see 9 of them. Yeah. Come to think of it. And then there's marks in between them, which serve to get you things of about like 0.2. There's 5 of them, 5 minor subdivisions between the major ones there. So, I was going to say we could do this up there, but we can live with this. I want to set up the length 12.4 on the slide. So what I'm going to do is slide the rule down until I bring the beginning of this B scale past the 10. Did I say 12.4? Okay, I've gone too far because here's 11, there's 12. There's 12. Where should I move to get to 12.4? I need 2 of those minor subdivisions. So I'll just put it on there, 12.4. Is that visible to you guys from the back? I've got 12.4 set up. I put the beginning of the B scale at the position 12.4. Okay.
Isn't that like 14?
Well,
no, sorry,
then
that
that
was
would be 13. There's 12, there's 13, that's 2 copies of 2 tenths, or 4.
That's the campaign, not it.
If I needed to do 12.3, I'd have to slide this guy in so it was like halfway in between those guys. Right about there. You can do that. So how many significant digits are in this number that I've set up at the beginning of the thing? Digits. How many digits are there?
It's 12.3, that is 3 significant.
3 digits. So I've got a 3-digit problem that can be visualized as a position on this top logarithmic scale. All right. So that's a tough one. Let's start with an easier problem. Let's do 2 times 3. I'll set up 2 back there. That is, I put the beginning of the B scale at 2, and then I come down on the B scale till I find 3. Oops, I moved it. Till I find 3, and then I look across from it and I see, wow. Right? So I added the length from 2 to 3, and I got the length for 6. What we're using there is a property of logs that I think you know, that the logarithm of a product is equal to the logarithm of the 2 pieces added up. So if you just interpret log meaning where is it written on that scale, where is the product written on that scale? It's at the sum of where the logarithm of A, where A is written on that scale and where B is written on that scale. The 2 scales are identical. By the way, one nice thing about it is once you've set up the first number, like I put the beginning of the B scale at 2, I can find 2 times 3 is 6, but I can also find 2 times 5 is 1. 2 times 5 is 1. What? But that's tampering, right? What's 2 times 6? 12. We were at 12 before. All right, so you can do all the multiplication problems involving 2.
Okay, so what's 2 times 1/10? So,
Let's see, there's 2. I would consider that number to be 1/10 rather than 1. So it's 2. Oh no, but it's points. So this is the weird thing about using a slide rule, is you've got to use your own noodle to keep track of where the decimal point is. This isn't going to tell you. In fact, I did 2 times 3 and got 6. The same exact setup would be there if I would throw doing 20 times 30 is 6. But now I have to go, okay, how many zeros are in that? You know what I'm saying? That the number, the main part of the number is there, but what's sometimes called the mantissa is what I'm able to find. We also need to know what's the power of 10. So that you do by hand, by brain. And it's really good that way, because when people get used to using calculators, you guys are all used to using calculators, right? Do you sometimes feel like that maybe you're not skeptical enough about the answer? The answer comes out and you just write it down because it came from the calculator, and you know those were handed down from God. You know, Texas Instruments, but still. We trust them, right? We just say, okay, there's the answer, write it down. When you were using a slide rule, you were mentally much more involved in the process, so you had an idea of the size of the answer you were expecting from the get-go. And if the slide rule told you something wildly wrong, you were much more likely to pick it up and go, oh, shit, I meant to set it on 12, not on 20. You know, move it over. You would catch your errors better. Now, true story, I was of the first generation where we didn't really learn to use these things. My dad had one, and he was really good with it. But, you know, calculators were just coming out. They were crazy looking things. I mean, they were really huge and fat. But, you know, to keep up with the Joneses, you know, I told you about how the slide rule people all had these things on their hips. Well, we had leather pouches for our calculators, and they were big and heavy. They had like 4 D cells in them. They were enormous boxes, and I got one that had trigonometric functions on it too. This was in the 70s, so it was pretty special. I could do Drake and exponentials. And my dad sat down and said, you know, I think I can beat you with this. And we wrote down a bunch of problems, multiplying, dividing at first, but then roots, extracting square roots, cube roots, things like that. We do that with slide rule. And he beat me, roundly. I mean, he was finished. Yeah, I was still halfway through the set of problems we decided on when he was done. Okay. The only thing that I could say is I had 7 decimal places for every single problem, and he had 3. But you know, he engineering solutions, which is what people care about these things. 3 decimal places is plenty. If you really care to have 1 more decimal place, most offices where you did, you know, these kinds of calculations, like at NASA or engineering offices, they would have special extra big slide rules. Not like this. This is a demo model for showing to students, but a nice 24-inch long slide rule, finely made, precision manufactured out of aluminum. Some of the ones you guys are holding are aluminum. That's aluminum. Not a magnet, you'd see it doesn't stick to that. But, aircraft grade aluminum that the ticket company always advertises. So why don't we try one? Not everybody has one. If you are not holding one yourself, go find somebody who is, and I want you to try to do how about 5.5 times 3.6 first. So, well, you know, you're going to have to trust the slide rule to give you the decimal places. You've got a tiny one. You want to use the big one? Sure. And then, next challenge. Now, this will be harder, but if you think your way through it, I think you'll get this. I'm going to show you what it is. Figure out what, 12 divided by 3.5 would be.
Can we opt to do this mentally?
No, you have to do it with the slide rule. And
Like 2 times 3. Take it to 0. You want
oh, that's something that somebody gave me at one point. You're gonna have to find somebody who's well, actually, you know, roughly that was
the line definitely
Yeah, and then like there's 24.
one on the screen.
I know that there was the
What's the last digit gonna be? Can you talk from the, or is that?
Oh, yeah,
Let's confuse ourselves. Who did you miss?
Holy cow, you guys are the huge ones. So have you found the A and the B scales?
Yes, it should be 18.8.
It's given a little, see how it gave a little bit to the left of it? That's really useful sometimes when you're doing division. You move the scale just off the top. It's a little sticky.
Oh, yeah, it has to be.
So there are actually, there's screws on here that you can crank on and loosen it up. So slides. So I mean, I need to put some wax on here. There's all kinds of trickery about how to take care of these things to get it to work better. But it also has this feature at the edge. There's this place where you can push through to get it started. And, the other end you can push out. They tend to get stuck in the middle.
Yeah, line 3.5.
Oh, yeah. Well, I saw you send out a note though, Sunday night or something.
I was getting there.
So you figured out how to divide? How do you divide?
Sure. Or you do, you have the 12 up top, you have the 3.5 lined up with that, and then you
I did.
Yeah, you set it up as if this was the result from doing the multiplication. So you set up the product over top of the divisor. And so it actually looks like a fraction.
I did it wrong because I did 3.5 and then found where.
Yeah.
You set up 3.5. at the base.
And then I found where you put 12.
Is it? Oh, yeah, I see what you're doing. Yeah. That is the same thing, because, you know, multiplication rates. Has everybody figured out how to divide? You have to read the manual for it. That's a,
I sit down already.
So, over here.
I can't figure out how to find that.
Well, you have to look at the numbers and go, they're all between 1 and 10. So the product will be between 1 and 100. Now you have to ask yourself, is it bigger than 10?
Yeah, that was pretty close.
Is the product of those numbers bigger than 10?
Yes.
Okay. So you're looking for a number between 10 and 100.
Right.
And it, you know, it's appearing, you can sort of see what the significant digits of it are. 1, 2, cycle. And you know it's between 10 and 100. That turns it into 18.8.
And
Must be 19. 19.
when it gets to the 19,
That makes
Oh.
I just don't like writing.
I'm going to need my glasses to do it.
I know this is like,
Yeah,
so that you get
5.5 is in the right spot. And then we'll come along on the second scale.
Well, my husband's science, so he was doing
periodic ones that, and I would only have one final. So I guess I had to read two science, midterm final. Final was just a section.
Most of the race could be just.
marker that would erase it.
Midterm and final, I have the same percentage.
That's a different ink. Marker.
I'll use it.
Please only
Midterm, whatever, they're like the
because once you
same.
work together, people just won't be thinking about it.
I'm used to reading this. We're almost out of time. I wanted to talk about different something today.
Oh, what's
Okay.
the
Did you put it up? 'Cause I only saw one of my grades, not math. I had only had one class in my second class.
A lot of chaos. Like,
That was a wig.
yes.
Not like.
He had a wig and of natural hair, so it looked really nice. He was a very particular man about his appearance. This picture I don't think does it justice. He had a very nicely styled goatee and mustache. You can see a lot of pictures. And that was the style that military officers wore. So he was trying to kind of make the same. So make sure if you're supposed to have that little accent on the final E. It's not Reen, it's Renee. Renee Descartes. There's something I should point out about the name. Sometimes you will see his name with D and then little e, little s, but the C gets capitalized. And in that variant of the way it's written, it's meant to imply nobility. It means he was the noble from the heart of the town. Lately, I'm seeing it always written with the C lowercase. Car?
Yeah, I was trying to figure out where.
Yeah, the Cartesian plane. Wait, you're a math major? You've heard of Cartesian?
No, I used to do that.
Oh, you've gone to the dark side. Okay. His father was named Joaquin. His mother was Jean. It's very sad. She had 2 children before her, 2 that survived. She had other boys that did not survive. And then so Renee was born with 2 older siblings, and then got pregnant again right away because he was only 1 year old when she died in childbirth. Ladies, that is a common way. When you read all this stuff about history, it's amazing how many women died in childbirth back in the 15, 16, 1700s, even 1800s, really even the beginning of the 1900s. It's just, I mean, it's not something that happens much anymore. It's a problem. He's described as a pale and sickly child who had a persistent cough. And it's thought that his mother may have had tuberculosis, which would have led to complications in labor. So possibly had tuberculosis as a child, but I guess he got better. You know, and that's strange because tuberculosis is usually untreated, something that just, you know, it's essentially into a permanent decline. He was a boarder at a Jesuit college, which before class I hadn't remembered the name of, but I've forgotten now, sorry. But yeah, I mean, you really want to picture Hogwarts. This is a bunch of little kids living with the schoolmasters and mistresses. Probably at that time all masters because it was a Jesuit school, so these were monks that were instructing the kids, but also acting kind of as parents. He went to Jesuit school at age 11. Because he was so sickly, and I think because his father was an important magistrate, he got permission from the headmaster of the school to stay in bed until 11. Okay. Everybody else had to get up at the crack of dawn and start doing stuff, but Descartes could hang out in bed, and that's a habit he developed for his entire life. He stayed in bed until 11 o'clock, never got up to do things until later, which I really like that idea. After getting out of the Jesuit school, he wandered for a little while, but eventually went to the University of Poitiers. Have you heard of Sidney Poitier? Famous actor. Same spelling, same name. Basically, this was to make his dad happy. He was not really interested in the law, but his father was a lawyer, and he wanted his son to become one and follow in his footsteps. And then he got the degree and never really used it. He became quite famous as a mathematician. Not immediately, though. So first, after getting his law degree, now I imagine he's 25, something like that, he started traveling around Europe selling his services as a soldier. This pale, sickly young kid who got up at 11 every day suddenly had become a master fencer and a military officer. And he served under two major armies at the time. Yours, Nassau. I keep hearing Nassau and thinking it's that island in the Caribbean, but probably not. There's a Nassau County. I think Nassau must be somewhere in France. Maximilian of Bavaria, I think they say in the U.S. That's a province in what's now Germany, within the Holy Roman Empire at the time, Germany. And what?
They make nice boats then.
Boats? Bavarian boats? They make nice food. They have really good cooking in Bavaria. Most German cooking sucks.
From Bavaria because it's a boat line called the Bavaria Yacht.
Oh, okay. Never heard that, but that's cool enough. So yeah, he's a soldier. After fighting for Maximilian, he wanted to go back home to Paris. But the plague, you've heard of the plague?
Black Plague.
The Black Plague was ravaging Paris at the time, so he said, well, maybe not. So he traveled around a bit more. I guess he was pretty flush at that point. I think Maximilian had paid him well for his service, so he traveled for a while, and eventually he did, another fact about his life, I gotta tell you. I mean, we're skipping all the good math, actually, right here. After traveling in Europe, by the way, he met some of the really important mathematicians at the time. Brother Mersenne, he met Fermat, but anyway. So all the good math is in there. Once he was really famous for his math and his philosophy, the Queen of Sweden said, I want that guy for my tutor, my private tutor. I want to learn geometry. And so she called him up to Sweden. He didn't refuse a royal decree. It didn't matter that it was a queen or a king of some other country. He still came. So he went to Sweden. Geographically, do you know where Sweden is compared to the rest of Europe? It's way up north, and there's an ocean in between. It would be possible to get there by traveling up through Russia and kind of drawing the home from your perspective. There. That's not the marker. Not to use that marker for the other guy. Okay, so Sweden and Norway hang down on a peninsula like that, and then the rest of Europe is like this. There's a little bit of a country that sticks up like that, gets really close to Sweden and Norway. Anybody know what the sticking up country is? Denmark, yeah, one of my favorite countries, so really cool people. And then like England and Scotland are out there somewhere, anyway. So to get to Sweden, you had to cross from, he had to leave from France, go all the way to Germany, get into Denmark, and then travel into Sweden.
you had to go by book. So here's Descartes, prissy, right? He's a short, slender guy, always dressed in black, very neat in his appearance. He did wear a sword, so he was trying to tell people that, he was not to be messed with. These tough guys on the boat that were taking him across to Sweden decided he was a mark, and they were going to rob him and throw him in the drink. And Descartes pulls out the sword and holds them all at bay and says, "No, gentlemen, you are taking me to my appointment," right? And they did. He was like, so it was like, I don't know, I get this picture of like the little mouse in the cartoon with the big cat coming after him, and he gets out his sharp stick and says, and Tom and Jerry, that's it, yeah. So anyway, he goes and starts tutoring Queen Christine. I think she was still Princess Christine at the time, but she was an early riser. She liked to get up at 5 and ride her horses at 7. So in between rising and getting her horse riding in, she wanted to get her geometry tutoring done. So Descartes had to stop getting up at 11 like he was used to and get up at 5 a.m. so he could tutor the Queen. Guess what happened? Yes. It killed him. It's also probably the case that he was, again, he had that tuberculosis lifelong, and it was doing okay in the warm climate in France, but Sweden's not France. It's pretty chilly up there. Long nights in the wintertime, and they can sit well with things. He wasn't that old. He was like 60. Which, most deaths, the life expectancy of people back in this era was not what it is for us today, by any means. But most of that was sort of infant mortality and people dying in warfare and disease as young people. Once you survive to 60, the likelihood was we're going to keep pushing on to the end of your 70s or 80s. So what's he famous for? Last thing? Cartesian plane. That's taking the carts part out of his name and turning it into an adjective. I can't express enough what a big deal this was, because up until this time, there was the algebra, the idea of equations that can be balanced, and there was geometry, and the two were completely separate. But once you said the plane can be labeled with x and y, and points on the plane correspond to values of x and y, algebra problems turned into geometric problems. And geometric problems could be turned into algebraic problems. And so the two subjects which were formerly disjoint became united. And there's a modern approach to this called algebraic geometry. I wish we were teaching you guys algebraic geometry in this school. There's things like, okay, somebody is in abstract algebra, who is it? You've talked about ideals.
Yes.
Things that you can draw in the plane, curves, or pairs of curves, or circles and circles, any collections of points in the plane. When you look at them algebraically, their algebraic representation is an ideal. So there's this beautiful connection between ideals in algebra and things that the curves and lines and things that we study in the plane. So there's a reason for all that ideal stuff. I don't know if they've told you that.
We've been keeping it abstract at this point.
They're keeping it abstract. Yeah, well, I mean, algebraic geometry is a pretty abstract subject, but the point is that you can connect not just regular, like quadratic formula level algebra, but abstract algebra with geometry through his invention. All right, so I will not see you Friday. Hopefully on the weekend, I'll be favoriting. I have a big stack of that to print.